Hey everyone, welcome to my channel and to the second episode of the Physics Professor Solves. Today we'll take a look at a problem that was brought to my attention due to some recent world events. Namely, more than a month ago, people around the world, or at least those of us who care, got fascinated by the results of the Romanian presidential elections in which they chose a professional mathematician, Nico Jordan, to run the country. Of course, that was not the main reason why he got elected, which probably had to do more with defeating the ultra-nationalist pro-Russian opponent and preserving the pro-European stance of the country, but for the purposes of this channel, it only matters that he's a mathematician. It's this guy on the picture that you see here. And I'm not even a Romanian, so I wouldn't pretend to know the subtleties of their politics, and I certainly didn't know about this guy before. But once he got elected, people started talking about him, and in particular about his two victories in the IMO, the International Math Olympiad. As you can see here, in 1988 and 1987, he got perfect score, 42 out of 42, gold medal. And specifically, people also noticed that in those 2 years, one of his opponents was Terence Tao from the team Australia, who also participated in '86. That there was this problem number 6 in 1988 that Terence Tao didn't solve, but Nico Jordan did. You see, problem number 6, perfect score. This is, of course, kind of a big deal for people on the internet, well, because Tao is quite famous by the mathematician standards and people tend to create heroes, etc., etc. But regardless, I've learned that the problem 6 from 1988, that was one that only very few people, including Nico Shore, solved, has somewhat of a legendary status as being extremely difficult and very challenging. Apparently, very few people that year solved it. So naturally, I decided to take a look and try to solve it myself. So let's go back to this problem. So this is a problem. Actually, I will open my notes. So a and b are positive integers, such that ab plus 1 divides a squared plus b squared. Now we want to show that this ratio, that according to the statement of this problem is an integer, is actually a square of an integer. Okay, let's start by denoting this integer as n. So we want to prove that n is actually a perfect square. Let's see. First, I want to rewrite this as an equation that doesn't involve any ratios. So I'm just going to write it as a squared plus b squared. Actually, hold on. Before doing this, let's see that the equation is perfectly symmetric. Under a exchanged with b. So without loss of generality, we can assume that a is less or equal than b. Let's see, can a actually be equal to b? Can we have a equal to b? And the equation will be 2a squared over a squared plus 1 equals n. Well, one obvious choice is a equals to 1. Then, of course, we get 2 times 1 squared over 1 squared plus 1 equals 1, which is a perfect square. Okay. Okay, so 2a squared equals na squared plus n. Okay, so now we know that one possibility is that n equals 1, right? In which case we found that a equals 1. Actually, another possibility, let's see, can n be equal to 2? If n is equal to 2, then the two sides cancel, no solutions. No solutions. And if n is greater than 2, then we get that n minus 2a squared plus n equals 0 again. This thing is strictly positive, so there are no solutions. Okay, so we found that if a equals b, then a equals b equals 1. I don't know if this will be useful, but it's just some special case. Maybe it'll help us later. In the meantime, we also kind of see that if n equals to 1, then there are not that many choices. Because... oh, yeah, well, we can rewrite the equation. Again, maybe it's not useful. N equals to 1, that we can have a squared plus b squared equals ab plus 1, or we can write it as a minus b squared equals 1 minus ab. And because this is greater or equal than 0, there's only one choice. There's only one possibility for positive integers a and b is that a equals b equals 1. Again, we came back to this solution. So now we can simply assume that a is strictly less than b and n is strictly greater than 1. Maybe we won't even need this. Anyhow, let's write this equation in the following form. A squared plus b squared equals nab plus n. Actually, let me go to the next page. I will write it as follows. B squared minus b times na plus a squared minus n. All right. A squared plus b squared minus nab minus n equals 0. Okay, so it looks like a quadratic equation in B. Perhaps I should even write x instead of b. So it's a quadratic equation in x. And we know that one solution is b. X equals b. We want this to be one solution, which is an integer solution. On the other hand, x, the solution can be written using the usual formula for quadratic equation as n squared a squared plus 4n minus 4a squared. All right, so in particular, we know that this expression n squared a squared plus 4n minus 4a squared must be a perfect square, where m is an integer, for x, well, for at least one of the two solutions to be b, because we know that b is a solution. Okay, but if n a is even, then n squared a squared can be divided by 4, and this is also divisible by 4. After taking square root, we get something even. Even after dividing by 2, we get an integer. On the other hand, if na is odd, then this is also odd, and this is odd. The square root is also odd. So odd number plus minus another odd number, we get an even number, and again, divisible by 2. Okay, so we can conclude that both roots of equation that's I will denote with a star are integers. Because b, which is a positive integer, is one solution. So it means that the second solution is also an integer. Well, okay, but we know. In fact, maybe I should use the Vieta theorem. We know that the second solution, which, how should I call it? Let's say that the second solution is, I'll call it Q. No, I don't want Q. I will call it K. It's an integer. And we know how it's related with it. We know that KB equals this term in the equation, so it equals a squared minus n. But then we also know that k plus b equals minus this term in the equation, whatever. So yeah, equals n times a. Okay. All right, so now we know that if we have a pair AB, where, okay, A is less than B, just in case, such that A squared plus B squared over AB plus 1 equals n, then we just found that there also exists another pair of A K, which solves the same equation, so such that A squared plus K squared over AK plus 1 also equals to n. Furthermore, we knew that n is positive, so because a and b are positive integers, so again n is positive. A squared plus k squared is positive. Therefore, we find that ak plus 1 is also positive. Okay. But then, what does it mean? It means that okay. I guess it means that k cannot be negative, right? Because recall that a is greater than 1. Thus, if k is a negative integer, then ak plus 1 would know. If k were a negative integer, ak plus 1 would inevitably be non-positive, so 0 or negative. Thus, we find that k is actually greater or equal than 0. Let's look. If k equals 0, if k were 0, then from equation kb equals a squared, then this implies that n is a squared. Okay, so it's total square. That's kind of what we need. Now, if k is greater than 0, then this means that ak are positive integers. Positive integers such that they obey the same equation. So whenever we have two integers a and b, we can find two other integers a and k that obey the same equation with the same n. Does it help us? I guess it must help us. It must help us in some way. Let's see. I want to say that, well, how does k compare to a and b? Let's see. How does k? Oh, no. I mean, oh, okay. Oh, I see. Okay, fine. Perfect. Let's look at this equation. So we know that k and b are positive integers. So let me write it as follows. K b equals a squared minus n. K and b are positive integers, so this is positive. It's positive, so a squared must be greater than n. But okay, but that's irrelevant. What I want to say is that a squared minus n is positive, yet it's less than a squared. So it means that kb is less than a squared, or k is less than a squared over b, but we assumed that a is less than b. So this being a times a over b is less than a. Okay, so k, let me write it in red. K is less than a. Awesome. I think we solved the problem. Let me clear it up, or just explain. We have a pair of integers a and b, positive integers, such that a is less than b, and a squared plus b squared over ab plus 1 equals n. And then we found that oh yeah, and in particular we're excluding this case, right? And n it is not equal to a squared. Then we immediately find that there exists another pair of integers, which I'm gonna write as k, comma a, also positive integers, such that k is less than a. Okay, so now the last step is basically to say the following. Consider the set. Let S be the set of all pairs such that of positive integers a and b, such that a squared plus b squared over ab plus 1 is an integer but not square. Then, in fact, did we use that a is less than b? Did we use that at all? I think we didn't really use that. Anyway, so okay, just for, let's say, a less than b. because a and b are positive integers, then there exists a pair which there exists a pair which minimizes such a with minimal a. So there must be such a pair. But then, by the above argument, there exists another pair, k comma a, such that k is less than a. This violates minimality of a and leads to contradiction. Contradiction, which is really contradiction to the assumption that such a set, I should have said non-empty, that such a set exists, which means that, in fact, this set should be empty. And then n is always a square. Okay. In fact, our proof, our solution not only proves that, but also shows that the only possible solutions to this equation with integer n are actually such that n is equal to a squared. Let me write it separately. So the only solutions are such that a squared plus b squared over ab plus 1 equals a squared, or let me rewrite this as a squared plus b squared equals a cubed b plus a squared, or in other words, we get that b is equal to a cubed. In which case, indeed, this is satisfied. Note how our special case that we looked at the beginning, a equals b equals 1, is included in this set of solutions. Okay? All right, so we solved the problem. We proved that the only integer ratios of a squared plus b squared over ab plus 1 are perfect squares, and we've actually shown even more that such perfect squares are equal to a squared when b is a cubed. Do I think that this problem is really that difficult? It's hard to tell now, but it probably is, yeah. It involves this rather non-trivial step of considering the set of all positive integers that violate the condition that we need to prove, that this where this is not square, and then showing that this set cannot have the minimal element. That once it has one element, then you can find always can find an element that's smaller. I forgot, there's some name for this technique, something like infinite descent or something. But anyways, it's a non-trivial step, but I think it's one of the techniques that are in the usual tool bag of students attending these Olympiads. Would I solve this problem back in high school? Honestly, probably not, because when I was a student, I was sort of specialized in physics Olympiads. Of course, I participated in everything, including math Olympiads, up to a certain level, but then at some point, starting at the national level and international, you really had to specialize and focus on one subject, and my specialty was physics. So I didn't know all these tricks back then. I probably wouldn't have solved it as a student. Now, of course, many years later, with all the experience in physics and math, as an active researcher, this feels a little different. But still, it was an interesting problem to look at and to solve. And hopefully this helps someone sort of showing how I think about these things, how looking at my thought process. Anyways, this is the end of the episode 2 of Physics Professor Solves. Please like and subscribe.